Okay, so before we state the fundamental theorem, we're going to need a lemma for it. Suppose we have a field extension and M is in script EF, as in the notation of the previous video. Again, this means that M is an intermediate extension. It sits in between K and L. Okay, that's what it means. M is an intermediate extension. And then we have an automorphism of L that fixes K. Okay, so an element of the Galois group. Okay. Then what? Well, we can apply tau to M. Remember, M sits inside of L. So let me actually just put this up here, maybe in orange. So K contained in M contained in L. Elements of the Galois group, they move L around, but they don't move K around. M contains K, so there's a chance that this tau is going to move our M around. So if we look at where tau goes, tau sends M, it's going to be some other field. Okay, so tau of M is going to be like over here. If we then look at the corresponding Galois group of L over tau of M, okay, then that is the same as taking the Galois group of L over M and then what's called conjugating by this element tau. All right, so again, this left-hand side here is the Galois group of L over tau of M, wherever tau sends M. And this right-hand side is tau, Galois group of L over M, tau inverse. So this is telling us how an action of an element of the Galois group via conjugation moves around the subgroup that we get according to the intermediate extension. All right, proof. For notational convenience, we're going to let M prime be tau of M. And we're going to take some gamma in M star. Okay, so again, that's the Galois group of L over M. It's something in this guy here. Now, what are we going to do? We're going to do a double containment argument. So, right, because we want to show these two sets, these two subgroups are equal. So take gamma there, and let's take some x1 in M prime. Okay, so M prime is tau of M. What we want to show is tau gamma tau inverse should fix x1 because x1 is in tau of M, and so if tau gamma tau inverse is honestly an automorphism of L that fixes tau of M, it should fix this x1 in tau of M. Okay, M prime is the image under tau of M, so there exists some x in M, in fact, there exists a unique x in M, such that tau of x is x1. Right? Everything in M prime comes from M. Then, if we apply tau gamma tau inverse to the element x1, what we want to show is that we get x1 out of it. So let's see that. We're going to do tau and then gamma. Sorry, we're going to do tau inverse and gamma then tau of x1. Tau inverse of x1 is x because tau sends x to x1. X is in M and gamma fixes all of M. So this is just x back. And then lastly, x1 is what you get when you plug x into tau, so we get x1. So this element fixes x1. x1 was an arbitrary element of tau of M, thus we conclude that tau gamma tau inverse is in this tau of M star. It fixes elements there. Similarly, by an exact, so let me say what this shows. What this shows is that we have one of the sides of the containment, namely everything here is here. Okay. So thus tau M star tau inverse is contained in tau of M star. Similarly, by by symmetry, we can sort of do tau of m star, tau inverse. We get tau inverse tau of m star. Tau inverse is contained in m dagger, or m star rather. And then we can, oops, should not be an inverse there. Excuse me. And then we can apply tau on the left and tau inverse on the right. And so what do we get? They cancel, of course. And this gives us the other direction of our containment, right? Yeah, this is supposed to be subset, sorry. No, this is element of, sorry, that's subset, that's good, sorry. All right, thus they're equal. Okay, so conjugating the subgroup that corresponds to a fixed field by an element corresponds to some other Galois group. The other Galois group is L over the image of the subfield under the element you conjugate by.